Hello, welcome back to Cracking the Cryptic, and an interesting looking puzzle today. But first of all, actually, we might try another one first. Hang on a second, though. On our Patreon page, we have now posted the solution to the hunt. So if you're a $3 Patreon, you can see the solution to the June reward puzzle hunt, Sudoku hunt, which was based on the Hitchhiker's Guide to the Galaxy. And you can watch basically how you were meant to solve that, including the key hint to understand the last puzzle and the twist in the tale of that hunt, as it were. So that's well worth your time, perhaps. Certainly congratulations to the hundreds of people who solved the hunt. There were maybe another 24 who sent in an answer that proved they'd solved all 4 puzzles, but didn't quite highlight the right information. So they don't make the cut of the people listed in the description field of that video. Anyway, that joins all our other stuff on Patreon. There's been a crossword posting this week, about a week ago, since Simon solved Sumanta Mukherjee's puzzle better than I did on the channel. Anyway, what I'm going to attempt to do today is a puzzle by Bram Cohen. Now, Bram's been in touch before. Bram interviewed Simon for a podcast he runs called Hard Problems, I think. Bram's involved in cryptocurrency, as far as I know. And anyway, he runs a podcast called Hard Problems. He interviewed Simon a while ago. I'm not aware it's been broadcast, and I don't think Simon is aware of that either. So maybe that's still to come at some point. I'm not sure. But anyway, thanks to Bram for involving us in that. I'm going to look forward to this puzzle today. But weirdly, while I was looking for this, because when Bram sent it to us, he didn't include the rule set, and I just wanted to check, because Cropkey has a couple of twists that we wanted to make sure about. I had to look it up in the Sudoku server, in the Discord server, and the puzzle before it, or the post before it in the Discord server, weirdly answered a question I'd asked a couple of days ago rather brilliantly, which was where I'd said, was 362,880, if I'm remembering the number right, the highest absolute number we'd ever see as a clue in a Sudoku grid? And Conflux had posted this, which was a puzzle called something like The Perfect KenKen it was from a, I'm trying to remember the name of it's a kind of puzzle sheet that is put out weekly by, I think it's by Jacob Cohen, and it's called something like Puzzles for Growth, or it's not quite that, so apologies for not remembering the name. I'll put it in the description field. But this, look at this number. This is absolutely brilliant. I don't know if you know KenKen, but the rules are similar to Sudoku. So we have a 6x6 grid. 1 to 6 appears in each row and column. Now, in the regions marked, we get a mathematical operation and the total of that mathematical operation. It's relatively simple in this puzzle because there are just 3 regions and they all have multiplication operations. So the product of all of these 6 cells has to be 16, for instance. The product of all of these has to be 45. And the product of the remainder, I'm not even going to try and say this number because I'd have to punctuate it with commas. But I'm also hoping not to have to do any divisions by that number when we go through this puzzle, but I believe it solves fairly straightforwardly. So let's just have a quick look at this before we get back to Bram Cohen, his namesake's puzzle. And I love the coincidence, actually, both of seeing this puzzle that answered the question I was asking brilliantly, but also the Cohen name as well. Anyway, 45 in 6 cells here. Now, the only factors of 45 that are in the numbers 1 to 6 are 1, 3, and 5, if we count 1 as a factor. And we can use 1, 5, 2 3s, and then we just have to use 1s. So if we're going to get 6 cells, there's 3 1s, 2 3s, and 2 5, and 1 5. So the 3 1s clearly have to be in these positions, the 2 3s in those positions, and the 5 there. And that region is done. And I think the same must apply to the 16. We've got 1, 2, and 4 as factors, and we can only do it in this region by having a single 4, a pair of 2s, and then 1s for the rest. So that's done all the 1s for the grid. Now, look, we get a naked single 6 here, and we can finish row 1 just using the numbers given. We can finish column 1. I bet we can do the whole perimeter. Yes, if I type correctly. We've got 3 and a 5 to go in there. And then look, we can place 2 in this row easily, and 4 then. Up here, 5, 3, and 6 to go in. So 6, 5, 3, 5, 6, 4, 2. And I mean, this puzzle solves pretty trivially, but I mean, it's a fantastic idea. And I am going to leave it to you to prove that the product of all of these numbers is the suggested number up here, because I don't want to bother proving that. But what a lovely idea, and what a perfect riposte, not deliberately aimed as far as I know. So anyway, let's go back to the real puzzle for today, Bram Cohen's Amigos, in which normal Sudoku rules apply. Black dots, this is crop key basically, normal crop key rules apply with no negative constraint for people who know that, but I will explain that black dots join cells with a ratio of 1 to 2, so that could be 1, 2, 2, 4, 4, 8, or 3, 6 in some order. White dots join cells with consecutive digits, so there's a difference of 1 between those. A 1 or 2 pair could have either a black or white dot. That's worth knowing, because obviously that would a 1-2 pair fulfills both of these rules. So compiler's choice. Not all possible dots are given, so there's no negative constraint in this puzzle, which can sometimes be very helpful. So do give it a go on the link under the video. I will also provide a link to the KenKen puzzle in our software, and the name of the puzzle sheet that it came on. Anyway, have a try. I'm going to try now. Let's get cracking. And we've got a very full box 5. Now, one of the features, I listed the possibilities on a black dot, and they include the numbers 1, 2, 3, 6, 4, and 8. What they don't include is 5, 7, and 9. So I'm going to ask the question, where can 9 go in this box? And that's quite interesting straight away. 9 clearly cannot go on any of the black dot cells because it's not allowed. It can't be in the middle of these two runs of 3, because it would need an 8 one side and a 10 the other side, and we're not allowed that. So therefore we've got 3 places left where 9 could go, but it can't go here because that would lead 9 to 8 to 7, and 7 can't go on a black dot. So 9's in one of these 2 cells, and this must be a run of 9, 8, 7 in some order. We can place an 8 in the grid, and in fact we've got a 9, 7 pair surrounding it. So that's a start. Now, there's quite a few runs of 3 ending in black crop key dot numbers that work there, but what's this going to be? If this was 6, 3, if this was 6, 3, you could not have a run of 3 consecutive numbers here, because you've only got 1, 2, 4, and 5 left to play with. So that's not 6, 3. So the numbers come from 1, 2, and 4. But how could they... Yeah, they couldn't be 2, 4, because again, you couldn't find a run of 3 from that, I don't think. If they were 2, 4, you'd have 1, 3, 5, 6 left. No way. So they can't include a 4. So that is a 1, 2 pair on a black dot. Now, 4 and 5 are definitely in this group. And therefore this is 3 or 6 on a black dot. So its other side must also be 3 or 6. So this number now must be 4 or 5. It sees both 3 and 6, and we can't have a 5 on a black dot. Bingo. So 4 there. 5 must go next to the 4. That's a 6. This is 3, and that's a 6. 4 on a black dot has 2 or 8 next to it. Do we know what this is? No, it's either 7, 8, 9 or 1, 2, 3 in some order. So the middle cell's 2, 8, and weirdly that gives us a 2, 8 pair, which we can't use. I can see this can't be a 9 because that would have to be an 8, and we've already got an 8 in the row. but oh, so there, but we do know it's going to be odd. So this is 2, 4, or 6 even. I don't think this is a parity puzzle. Ah, look at 6s here in columns 4 and 6. Where does the 6 in column 5 go? One of these 3 cells, but it can't be there because that would need a 3 on the croppy dot, so on the black dot. So 6 is down here. It can't be with a 5. We've already had a 5 in the column. So it's a 6, 7 pair, and 7 can't be on a black croppy dot. So we get a start there, 6, 7, and 3. Now we've got a 4 to... Okay, what's this pair? It can't be 4 and 5 because the 4's there. So it's either 1, 2 or 8, 9. I don't know how to tell, and they're very different. I don't even want to pencil mark those. Okay, 5 though. Oh, right, yes, 5. Where does 5 go in this column? Right, it can't go down here because 6 and 4 have been used in the column. It can't be on a black Kropke dot, so 5 is up here. 5's in one of these 2 cells. It could be on the white Kropke dot. 5, 6, 3, 4. So there's no negative constraint, so we can't just fill in a 4 here as I... Well, actually, that wouldn't work at all if there was a negative constraint. Never mind about that. These are from the 1, 2, 4, 8 set, of course. Ah, actually, yes, that means I've just noticed something else. You can think of the sets of digits that can go on black Kropke dots as either the 3, 6 pair or everything else is from 1, 2, 4, 8 in various pairings. Now, this black Kropke dot cannot be 6 or 3 because of those. So those 2 also come from the 1, 2, 4, 8 set. And now this pair can't because we'd have 5 iterations of the number 1, 2, 4, 8 across 4 cells. So that's a 3, 6 pair there. With that 3, 6 pair here, that means 3 and 6 have to be in these 3 cells. Therefore, at least one of them's on the black Kropke dot, and therefore both of them are on the black Kropke dot, which is a lovely way to conclude that, I think. That doesn't really help with this. That can be 2, 4, 5, or 7. So what else can we do? 3, 3... No, not sure there. 7. Okay, across this row, we've got 3 and 6 definitely used. Then don't know there. So this could be, well, could be various possibilities, just not sure. Right, we need to find some other way to get things going. Right, this cell sees 3 and 6 in the column. So again, those numbers are from 1, 2, 4, and 8. And the same is true up here, although that can't be 4, so this can't be 8 accordingly. 5, 6, 3, 4. Ah. So what? Oh, so that's not 7. Right, 7 is confined up to one of these 2 cells by that 7, and that fixes this 9, 7 pair. And now 9 in this column has to be on these dots. Right, so it's a 9, 8 pair. That's going to fix... Well, no, it doesn't fix. It only fixes that those are a 1, 2 pair. Anyway, 9, 8. So this could be 9, 8 or 7, but we've already got a 7 there, so it's either 9 or 8. 9, 8, 7, 3, 6. So this is either a 5, 4 or a 2, 1 pair. This doesn't quite resolve that. 7, 6, 3, 8, 9. We've got 1, 2, 4, and 5 to place in the box. Now, 5, 6, 8, 7 have been used up. So this pair can't use 9 because it can't use 8. So they must be from 1, 2, 3, and 4. Ah, yes. Okay. So this white dot, oh, that's very interesting. This cannot be, this can't be 1, 2, or 4 because that would cause a quadruple of 1, 2, 3, 4. And that mean that this had to be one of those numbers or 5, and that would be impossible. So that is 8. That makes this 4. That makes this 7. 7, 8, 6, 9, 3. So that is 1, 2, or 4. Now we've got our 1, 2, 3, 4 triple, quadruple. We know that 3 there has to be on the dot, so 1 isn't. This must be the 9 that we need to fill the region, the box. Oh, look, there's a 1, 2, 4, 8 quadruple down here. My goodness, that's very handy because it makes this a 9 at the bottom. So that resolves that. 9, 8, 7, 3, 6. Everything here is from 1, 2, 4, or 5 in the bottom row. That's a pair, so that's a pair. If that's a 4, 5 pair, that's 2, 1. But if that's a 1, 2 pair, that's 4, 8. And they all seem possible. This, I'm going to fill in the possibilities now. I've been avoiding doing it, and they don't really help much. 3, 6. We've got 7 and 9. Okay, I've just noticed 7 is in one of those two cells. One of those two is what I'm trying to put it in. Therefore, it's not there after all. We've got 7 and 9 to put in up here. Ah, and that's quite interesting. And quite difficult to do. Right, yes, 7 and 9 don't appear in these 6 cells. So they must appear in these 3. So this white dot has either a 7 or 9 on it. And therefore, since its constituents can't include a 6, they must be from 7, 8 and 9. But they are 8 and one of 7 or 9, so the other of 7 or 9 goes here. And we end up with a triple, a 7, 8, 9 triple, which makes this not an 8, which gives us a 1, 2, 4 triple and makes this a 5. I may be overcomplicating some of these steps. That is entirely possible. 7, 8, 9, 3, 6. So still not sure about 1, 2, 4 and 5. 4 must be in that row. Still don't know. Okay. So what else can we do then? Oh, that can't be a 4. 4's in one of those 2 cells. 3, 6, 1, 2, 4, 9. 3, 6, 9. Okay, I don't really know how to progress. So let's have a look at this quadruple again. 1, 2, 4, 8, 9. 1, 2, 4, 8 in the quadruple. 9 there. So we have 7, 3, 5, and 6 to place. Doesn't look that helpful in the column. Maybe it's time to think about whether this is 1, 2, 3, which would leave this as 8, 7, 9. Oh my goodness, okay, that doesn't work. That's handy. Right, if that was 1, 2, 3, you'd get an 8 here, because it can't be 2. This would have to be 7, and this would be 9. But now, this would be 6 on the white dot. And where would 1, 2, 3 go in this box? They can't all fit in there once that's 6. So this isn't 1, 2, 3. This is a 7, 8, 9 triple sequence. That becomes 2. That takes 2 off this dot, which must now be 4, 8. And that's very helpful. We get 1, 2 there. We get a 4 here with a 5. Take 5 out of that set. So now that's a 2 or a 4. This must be 3, therefore. These are a 1, 2 pair. That's a 5, 7 pair. Can't really disambiguate these yet. This has become a 1, though. That's helpful. 2 there. We take 2 out of all that cells. That's a 3, 4 pair. We get a 1. This 2, 1 are resolved, and so this 2, 1. This is now a 1, 3 pair, so that's not 7. This isn't 6. It's also not 2. So that's 4. That gives us the 3 and the 1. That's a really pretty way of everything getting sorted out, actually. Very nice. Elegant puzzle. Right, in this column we've got 3, 6, 4, 1, and this is a pair. So it can't involve 2 or 5. It must involve 8 and either 7 or 9. That one can't be a 7. So where does 2 go in the column? It goes here. 4. Ooh, okay, that didn't get everything done, did it? Now what about this? Can't involve a 1, a 4 or a 5. Not very restricting. That's 5, 7, 8 or 9. Okay, I'm grinding to a bit of a halt. 1 is over there somewhere, and then the rest of this row is 3, 5 and 7. 3, 3, ooh, one of those two's a 3. So that can't be an 8 anymore, so we know where 8 is down here. So 8 is in one of those two cells. Ooh. Can nearly rule it out of that one, but not quite. 7, 9 form a pair in this column. That's not going to help, is it? Oh, yes it does. This is a naked single. It sees, oh well, it sees 7, 9, 7, 8, 9, 3, 1, 2, 4 and 5. So that has to be a 6. 6 there. We get a 6 up here somewhere, which doesn't resolve anything. 5. That is 1, 2. Ah! This is almost a naked single. 4, 6, 7, 9 pair and 5. And 1, 2 in the row. So 3 or 8. Let's just keep going with this thought. 1, 2 or 3 there. And at the top, 4, 6, 5, 7, 9, 1. So 2, 3 or 8. And it's on a white dot. Now this can't be a 1, but it could be a 2, 3, not a 4, a 7 or 9. Wow, this is getting confusing. 1, 2, 7. Certainly getting held up a bit towards the end of this puzzle. Oh, 7, 8, 9's a triple up here. Oh my goodness. Okay, sorry I hadn't spotted that. Having done the work on the 1, 2, 3's, I really should have been able to see that a bit more clearly. 7, 8, 9. So this is a 5, 6 pair. Also, we get a 4, 5 pair over here. This is part of a 1, 2, 3 set. That can't be a 3. That can't be a 3. 2, 1. Oh, has this not finished us off? No, it really hasn't. Right, let me... It must have proved something over here. That can't be a 7. That's a 3 or a 6. Yeah. 5, 4 is up here somewhere. That doesn't help. It's all about this pair. Can that really be 2, 3? Then we'd have 4, 6, 7 or 9 here. 7 or 9 here. That would make this an 8. But the alternative is 8, 7, 9 as a triple there. 1, 5. And then you'd end up with 2 here. And why not? That seemed to work fine. Have I missed something on a white dot that's giving away the result? No, I don't think I have. Wow, what am I looking for now? I don't even know. Sorry about this. 1, 3, 2. That can't be a 3. So 3 is definitely in one of those two cells. So if it's there, I don't know. That doesn't seem to fix anything completely. 1, 3, 2. Oh, look, there's a 5, 7 pair there. Ah, right, okay. Sorry, that took a while to spot. So we get a 5 there. Right, now we know where 3 is. That's a 6. That doesn't read across into there yet. It's definitely a 1 here. We knew that before. 3, 1, 6, 2. I thought this was going to have resolved it. And it hasn't. 5, 7, 8, 9. That's an 8, 9 pair. So this is 7. That still doesn't quite resolve it. This could still be 8, 9. But now this is 8. That makes this a 3. Now this can't be a 2, 3 pair. So it must be 8, 9. And I think we are finally into the home straight. So we get a 4 and a 2 in the top row. We've got 5 there and 9. A 5, 6 pair to go in. This is now a 1, 7 pair, which I can't resolve, but I can do that for 5. I can do this 9, 7 pair, and therefore this 9, 7 pair. 4 is placed here. 1, 2 pairs still to go. Right, the 1, 7 pair is done. That can't be a 1. This can't be a 3. So that's where 3 goes. Yes, I can do the 1, 2. Right, so that's all the right side boxes done. These are straightforward now as well, and I'm suddenly finished. That's a very neat puzzle by Bram. Not certain why the Amigos are involved. I suppose those 3s and 6s were quite important early on. I'm not sure if that's what it was about, the 3 Amigos. Anyway, super puzzle though, really entertaining. Certainly very well paced in that not too hard a break in, but also not too easy a finish as well. So good stuff. Thanks as always for watching, and very much hope to see you again soon on the channel. Bye for now.